Hi everyone, this video is the next in the series of the SDRs and VORs series. So on President's Day, my stepdad and I rented a plane and went flying to collect some data. So he's working on his certified flight instructor certificate and needed some right seat time. And I hadn't flown in a month or two, and so I definitely could use somebody with some more current experience with me. So it definitely worked out really well. And also I had some time to focus on the computer while he was flying. So what I did is I used an antenna and I hooked up my low noise amplifier that I have shown in some other videos that I'm selling on Tindy, right up to the antenna, and then I used the same RF power splitter that I showed in the other Aero Commander charter flight VOR-SDR video, and then I used two RTL-SDR dongles, and I was able to record simultaneously from sporadically, but at one point I do have 3 simultaneous VOR receptions. I think Newport and Corvallis and Eugene. And then as a bonus, I actually got some samples from the Newport Instrument Landing System Localizer. And that's something that John Milesbury on Twitter had asked about when he saw my first VORs and SDRs videos. He was really interested in seeing some localizer audio, localizer samples. So anyways, I haven't done the navigation determination from the VORs yet. I have done the post-processing, and that data looks good for the VORs, but this video I really want to talk about the localizer. So let's do this one more like a tutorial way. So I'll explain to you what I'm doing as I'm doing it. So first things first, at least the way I do things first, is when I'm dealing with a signal that I don't really know what it is or what it's all about, I pretty much just look really closely at the spectrum. Now I know this is a localizer, so I kind of know what to expect. But all the same, we're going to look at it. I like to turn average on and turn peak hold on. The throttle is set for 1 because if it's not throttled, then it just pegs your system and it's hard to do much else. But I also have set it to 4x real time, so we don't have to sit around and wait for the full duration. It's a 20-minute long. I think it's about 20 minutes, and so this will take it down to 5, and I'm going to obviously edit it down to be even shorter. So we're just going to call this visualize, and I promise that I can type, and then something went wrong. So what do we have here? Oh, I don't know why this default is changed, but I have to change it on every one now. Okay. So here's our spectrum. I've already centered up the baseband, so the signal we're looking for is in the center. You'll notice there's this funny bump that just sort of marches through the frequency. I have no idea what that is. It's not uncommon to see those when you're doing SDR. That little pulse that you just saw there, that was a result of somebody transmitting on a nearby frequency, and it reduced the sensitivity of the whole device. Now you can see we're starting to get a signal here in the center. You can see the spike of the center frequency, and you can also see the sidebands. And so that's pretty encouraging. We'll give it another minute here. You can also start to see some sidebands now here at, what is that? About 1 kilohertz, I would say, on either side. So that's also really encouraging. Those sidebands are really quite strong. We could also see that, if we do 2.5 kilohertz on either side, we should be able to capture the whole signal. And now the signal is very strong. You can see how those sidebands shot up. So even with 4x throttle, we're using the system strongly enough that it's not being so responsive. Okay, so that's all I need for now. I know how wide the signal is, so I'm going to chop that down even more. So we're going to keep the throttle block. I'm going to get rid of this connector. We're going to low pass filter, and we want it to be, let's call it 4 kilohertz. So we're going to divide 32 by 8, I think. Yeah, there we go. And then we're going to use a cutoff frequency of 2.5 kilohertz with the 500 hertz transition. I choose the transition frequency somewhat. I should say actually we only want to do 1500 hertz because we're doing a 4 kilohertz sample rate. And if we do any more than 2 kilohertz, we're going to get aliasing. And so if we do 1500 and 500, then all of the signal will be below the Nyquist bandwidth. Okay, so we wanted to take sample rate the same. Going to do 8 decimation, and then the output frequency of this will be 8 kilohertz. And then we need to make sure we do divided by 8. And I meant to say 4 kilohertz. Okay, sorry. So that I realized that was confusing. So let's go ahead and try that out. And I'm actually going to speed up the throttle just because I don't want to have to wait that long again. Okay. So we can see that on the sides here, the power tapers off really quite steeply before our Nyquist bandwidth limit here on the sides. And so that's exactly what we're looking for. One thing to notice too is that we've got these spiky tones here on the sides. And those are really quite weird, aren't they? Here's those, basically 1 kilohertz sidebands I had mentioned. We can notice that we're not quite tuned in the center, but I think that'll be okay. And now the signal is really, really strong, remarkably strong. And we have all of these intermodulation tones that are appearing out of that. And so that's really interesting, and that's, pretty good news. Okay, so some things that I can tell. This signal is symmetrical around the carrier, and to me that says it's usually AM. So I'm going to go ahead and put in an AM demodulation block and then capture this as a wave file, and then we'll look at the baseband signal. Okay, so we've got our wave file, we've got our FFT on the baseband, and we're going to run this, and in post I'm going to sync the audio up. My screen capture program doesn't do audio on its own, so you'll be able to hear the audio. And just so that I can comment it, I want to listen to the audio as well. So I'm going to do that. Okay. Now, one thing I have to do is I have to put the throttle back to the regular sample rate, otherwise the audio won't work. So I went ahead and doubled the bandwidth of all the demodulation and the wave sync and audio sync. 4K was probably unnecessarily low bandwidth. It was fine for when I was running the throttle rate high so that I had more CPU to devote to it. But there's really no reason to run it that narrow band. So now we can see those peaks again. We've got, one of these is about, 90 hertz or so. The other one's up here at 150. We're starting to see evidence of a new peak popping up here at around a kilohertz. And if you listen very carefully, you can hear some Morse code. So that's dot dot, dash dash dash, dash dot, dot dash dash dot. Now, if we pull up AirNav, you can go down to ILS or Localizer runway 16. And we can see Localizer, dot dot, dash dash dash, dash dot, dot dash dash dot. So we know that that is the ILS Localizer for Newport. That's really cool. So you can also hear those two tones, the 90 hertz and the 150 hertz tone, and you can hear them beating against each other. So let's look up, we know it's an ILS localizer. So let's go to the trusty Wikipedia. And we can see that there are two lobes of the localizer that show us where the signal is, or where the plane is in relation to the localizer. So we can see that if we're way over here on this lobe, that we are going to get mostly the 150 hertz tone, whereas if we're over here, we're going to get the 90 hertz. And in the center, we should get equal amplitude of both tones. So we can see here that they're almost equal, which means that we were, at least when they were almost equal, we were right on the center of the localizer. And now we're getting further and further away from the center. And that's perfect. That's exactly what we want. So I've gone ahead and created a flow graph that does a lot of cool processing to make this work for us. So what I do is, this is just that same raw file. We throttle it, demodulate it, block DC. I just sample the audio so that I can hear the Morse code, hear what's going on. And then we have two bandpass filters, very narrow bandpass filters. We have an 80 to 100 hertz bandpass filter and 140 to 160 hertz. So they're both 20 hertz wide, centered on those two tones. And then what we're doing is adding those two together and then doing a waterfall sync. And the only purpose of that is so that I can visually see the relative amplitude. Also, these are, you can see they're real to complex filters, and that's just because I really want to do all of the rest of the stuff in the complex domain or whatever, because then I can do complex to magnitude to get a good power out of it. So I subtract the two signals, and that will give me the relative. Above 0 would be one was stronger, below 0 would be the other is stronger. I low pass that to be a literally 1 hertz signal, and I sample that 1 hertz signal at 1 kilohertz, and then I just put it out on the scope so we can see that working. One thing that bugs me about this display, and I'm not really sure exactly what the problem is, but we've got 1 kilohertz in the waterfall, 1 kilohertz in the signals in the scope, and I tried to make the time scale in the scope equal to the time scale on the waterfall. So you see the waterfall says 240 seconds, and so I'm assuming that this top line is 260 seconds, which is the same as right here. So that would mean that this little spike right here is the time constant of the DC block here. You can think of it just like a capacitor, right? So when you have a step on a capacitor, you get an impulse like that. So in theory, this little impulse should hit this right edge at the same time as it hits the top edge of the waterfall. But you can tell there's no way it's going to be even close, because this is 170 seconds, and so it should be over here by now. But it seems like it's moving roughly half as fast on the scope plot as it should be. So now we can just barely start to see the faintest traces showing up in the waterfall. And we can also, start to see a few little flickers of life coming on this display. A limitation of this method, which is similar to the limitation of the method I use for the VOR, is that 0 from lack of signal is indistinguishable from 0 due to being on the center of the localizer. In the VOR's case, it was 0 was north, and so north is indistinguishable from no signal. So as these relative intensities start to change, you see the 150 hertz is starting to get more intense. You can see that the signal deviates away from 0. And then it gets back as the strength of the 150 hertz declines and the 90 hertz increases. So what we did here is essentially either we crossed the center path of the localizer, or this is an errant reflection or something, and it wasn't actually the true path of the localizer. Something that's interesting about localizers is that they're very sensitive to reflections. Unlike VORs, which are fairly immune due to the way that the radial is encoded, localizers don't have that immunity, so it's very important to ensure that you don't get reflections. Okay, so now we can see that we've got a pretty clearly obvious signal on the 90 hertz. And going back to the Wikipedia, 90 hertz is left of course. So I suspect that this is the true signal. And because I was approaching Newport from the east, and it's a north, thresholds to the north of the runway. So I do believe this is the true signal. And then I think that this is us crossing the localizer past Newport. And then we turned around and we're flying back to Corvallis. And so now I think we're on the back side of the course, and we're going from west of Newport back to east. We're going to see the signal go up, high intensity again. on the left, of course, and then go back down. And I think that this deviation back down is actually due to us leaving radio range. And so we should see the signal strength taper off. And so what this shows to me is this is a perfect example of us, starting left of course, crossing through center line, staying right of course, and then turning around, and then crossing the center line again the other direction, and then the signal tapering off. And then here I think we're seeing some more sort of reflections and errant signal strength just as we're flying away from the station. So here's the same data one more time, and I apologize for the sort of cheesy animation. I didn't realize that I was going to be covering that up when I recorded these two separate things. So there's the same trace as before, and I've added a trace for absolute power, which is the sum of the power of each of the side lobes there. And so as the airplane gets close to the field, you can see the power starting to increase. And it goes quite a bit faster. Obviously, the closer we get, it should be close to exponential. So now we're basically just now in the left of course lobe, as strong as it will be, crossing. And then now we're in right of course, and then crossing again just now, and then back to left of course. And it should be noted that the antenna array should be at the south end of the runway here, and it points north. But these antenna arrays are not so directional, so we actually do get some power out of the rear. And you can actually sometimes navigate with that as well. Well, I think that's going to be it for this video. I'm going to publish the source files and the flow graph just like the VOR video. I've still got a lot of work to do on that VOR data in that other video, so stay tuned for that. If you like this stuff, please let me know in the comments, like the video, and subscribe. I'm sort of do this stuff in the dark. I do what I like to do, what interests me, and I have obviously a lot of varied interests, so whatever you have questions about, want me to look into more deeply, just please let me know. The reason I am doing any of this analysis at all really is because John Malsbury on Twitter suggested I look into it, and so I thought that was a cool idea, and I went for it, and I'm glad I did. It was really cool and surprisingly easy to do. This only took me maybe 2 or 3 hours, literally on a sick day from work, to figure out how to do all the demodulation of it. So yeah, thanks for watching.